Dear viewers, in this series on silicons and phosphazines, up till now we have been discussing silicons. In today's episode, we will be discussing phosphazines. So, the lecture plan for today's lecture is this. First of all, we will be discussing phosphazines and their methods of preparation. Then we will discuss their physical properties and chemical properties, their structure, the nature of bonding in phosphazine, D-pi, P-pi bonding model of cyclo-triphosphazines will also be discussed, and then we will discuss the Dewar and co-workers model of phosphazines. And finally, we will end this lecture with the uses of phosphazines. Coming on to polyphosphazines. Phosphazines or polyphosphazines are also called phosphonitrile compounds. These are the inorganic polymers which contain alternate phosphorus and nitrogen atom. Therefore, the name phosphonitrile, which indicates that these contains both nitrogen as well as phosphorus. The general formula for phosphazine is NPR2 whole N. N is a nitrogen, P phosphorus, and R can be any alkyl group, phenyl group or halogen atom which is attached to the phosphorus. Each macromolecule of phosphazine contains 50,000 or more repeating units, that is, we can say that the polymer phosphazine contains 15,000 units of monomers. Commonly these exist as cyclic, that is in the form of trimer or tetramers, or in linear polymers form. On heating chlorophosphazines, these are transformed into an elastomeric material which is called inorganic rubber. Here we can see we have the structure. This one is the cyclic trimer. This is the trimer because this contains 3 nitrogen atom and 3 phosphorus atom. We can see each phosphorus atom is bound to 2 R group also. This is the cyclic tetramer. Tetramer because it contains 4 nitrogen atoms and 4 phosphorus atom. Again here also we can see each phosphorus atom is also attached to 2 R group. The R, as I have already said, it can be alkyl, phenyl, or it can be any halogen. This is the linear polymer, or we can also say that this is the general formula of the phosphazines. Here we can see nitrogen is attached to phosphorus and phosphorus is also attached to 2 R groups, and this is a monomer unit which contains n, when n number of units connect together they form the polymer. Phosphonitrile halides have R, that means the phosphonitrile halides, that means the ones containing halogen. In those halogens, the halogen can be, that is the R can be fluorine, chlorine or bromine. Among these, the chlorides have been extensively studied, that is when the R group is being substituted by chlorine atoms, such type of phosphazines have been most broadly studied, and among those the trimer and the tetramer, that is NpCl2 whole thrice, this is a trimer, and NpCl2 whole 4, this is the tetramer. These two have been the most widely studied phosphonitrile halides. Reaction of PCl5 with ammonia, or we can also react it with NH4Cl, it forms a white crystalline solid. We can see here this phosphorus pentachloride, it is PCl5, it reacts with ammonia, or we can also react it with NH4Cl. It forms a mixture of cyclic trimer, cyclic tetramer and some linear polymers, and this mixture is white crystalline in nature. Classification of phosphazines. The phosphazines can be classified into 3 types. The first is polyhalophosphazines, that means the R group in these is substituted by some halogen. The next is simple polyphosphazines, and the third is substituted cyclic phosphazines. Coming on to the preparation of phosphazines, first of all we will take the preparation of polyhalophosphazines. To prepare polyhalophosphazine, we treat PCl5 with excess of ammonia in the presence of chlorobenzene or carbon tetrachloride, and it is heated to a temperature of 120 to 140 degrees Celsius. So, we can see that n number of phosphorus pentachloride is treated with n number of ammonium chloride or ammonia. We can also take ammonia in place of ammonium chloride, and we heat the mixture to 120 to 140 degrees Celsius, and this polyhalophosphazine is formed. A mixture of cyclic trimer and tetramer and sometimes linear polymers are also obtained in this mixture. The second method is by treating P3N5 whole N in chlorine at 700 degrees Celsius. We can heat P3N5 whole N in presence of chlorine at 700 degrees Celsius. Again we obtain PnCl2 whole N. This N can be, it can have any value. If it has a value of 3, then it will be a trimer, and if it has a value of 4, it will be a tetramer. The third method is that the preparation of chlorofluoropolymer, that is PnFCl whole 4, this is a tetramer. It is prepared by heating the trimer PnCl2 whole thrice with lead difluoride. In this case PnCl2 whole thrice, this is the trimer. It is heated with lead difluoride, and what happens here, one of the chlorine, it is replaced by one of the fluorine. So, we get PnFCl4, tetramer is formed and other products are also formed. Trimer phosphonitrile chloride can be formed by treating S4N4 with SOCl2, that is thionyl chloride in PCl3. So, S4N4 is heated with thionyl chloride and PCl3. So, we obtain a trimer, that is PnCl2 whole thrice. Some other products are also obtained. Now, the second type of phosphazines and their method of preparation. First is PnCl2 whole thrice, that is a trimer. It is a starting material for different polymers. On industrial scale, it is prepared by reaction of phosphorus pentahalide with ammonium chloride in an organic solvent like chlorobenzene or carbon tetrachloride. So, PCl5, when it is reacted with NH4Cl ammonium chloride, we obtain PnCl2 whole thrice, that is a trimer is obtained. The purified compound is then heated in the molten state in a sealed vessel in the absence of moisture for several days at a temperature of 200 to 250 degrees Celsius to bring about ring opening and polymerization. The resulting dichlorophosphazine is dissolved in a suitable solvent and produces a number of other interesting polymers via nucleophilic substitution reactions. So, here we can see this is the cyclic trimer. It is heated at a temperature of about 250 degrees Celsius in a sealed vessel which is freed from moisture, and the ring opening takes place. This compound is further heated and cross-linked inorganic polymer is obtained. Similarly, if we take tetramer, the same type of reaction takes place, the ring opening takes place. The chlorine atom in polydichlorophosphazine can be substituted by alkyl phenyl alkoxyamine or substituted amine groups by the treatment with the appropriate reagent. So, here we can see we have this phosphazine. If we react it with, this is secondary amine. So, this chlorine group, it can be substituted by the Nr2 group. If we react it with the sodium alkoxide, this chlorine group can be replaced by the OR group, that is the alkoxy group. If we treat it with primary amine, that is RNH2, again this chlorine atom can be replaced by NHR group. And if we treat this polymer with some organometallic reagent like RM, R is the alkyl part, M is the metallic part, then we can replace this chlorine atom by the alkyl group. Bulky and weak nucleophilic groups do not replace all the chlorine atoms at mild reaction condition due to steric hindrance. So, we can say that the steric hindrance is basically the crowding. If a big bulky group is attached, then it creates steric hindrance. So, steric hindrance slows down the reaction rate after the introduction of a bulky group. Because of this bulky group, other group they cannot come closer to the central atom, and so the reaction does not take place. So, in such condition, like for example, we have NpCl2n, it reacts with diethylamine. So, one chlorine atom per phosphorus is replaced. The remaining chlorine, that is the second chlorine, it can be substituted by the treatment with less hindered nucleophi like methylamine or short chain alkoxide or alkyl or aryl organometallic reagents. So, we can see here we have this polymer. If we treat it with R2 NH, and if R is this is the secondary amine, and if R is any bulky group, R can be ethyl or higher alkyl group. If it is bulky, so only one Cl will be replaced by this R group. So, we have Nr2, the second chlorine is left unreacted. So, now what happens? We can introduce some short groups or lighter groups in the place of this chlorine atom. So, if we treat it with primary amine, this is R dash NH2, here R dash is a small group. So, this chlorine will be replaced by the primary amine group, that is NHR dash. If we treat it with sodium alkoxide, so this chlorine atom will now be replaced by the OR dash group, that is the alkoxy group. And again if we treat it with this organometallic compound, so this chlorine will now be replaced by the alkyl group. So, this way we can introduce the lighter group in the second position. Organometallic nucleophiles such as Grignard reagent and organolithium reagents react in a complicated way. For example, NpCl2 whole N reacts with RMgX, that is the Grignard reagent, and replace the chlorine atom by the R group, and is also accompanied by the cleavage of phosphorus nitrogen bond in the skeleton. This we can see here, this is the polymer of the phosphazine. When it reacts with RMgX, that is the Grignard reagent, one of the chlorine atom, it is replaced by the R group of the Grignard reagent. If the reaction is further carried, what happens? The bond between the nitrogen and phosphorus, it gets broken and another R group is being introduced here. Now, the third type of phosphazines, that is the cyclophosphazines. Coming on to their method of preparation. The organic substituents are introduced at the cyclic trimer phosphazines. Then the ring opening polymerization of the substituted cyclic trimer takes place. The ring opening tendency decreases as the halogen atom in the trimer are replaced by the organic group. This is the cyclic trimer. If we react it with phenyl lithium, then one of the fluorine atom, that is one of the halogen atom on this cyclic trimer, it is replaced or substituted by the phenyl group. Now, if we again heat this, then the ring opening takes place. Now, after the ring has been opened, we can treat it with some group, like we have in this case we have sodium alkoxide, and all the remaining fluorine atoms or all the remaining halogen atoms, they can be replaced by the reacting groups or the reactants. So, alkoxy group is introduced here. Limitation of this method: the tendency of polymerization decreases as more and more halogen atoms in the polymers are replaced by organic group. That means, if the halogen are present in the polymer, the reaction rate would be high, but if the halogen atom is replaced by the organic group, and as the number of organic group they keeps on increasing in this polymer, the reaction rate keeps on decreasing. Example: the cyclic trimer, which contains 6 methyl groups, that is NP, nitrogen phosphorus methyl 2 whole thrice. This is a trimer, it contains 6 methyl group. It undergoes ring-ring equilibration to the 8 membered cyclic tetramer on heating, but it does not polymerize to higher polymer. So, we can see here we have the cyclic trimer. This trimer, because here halogens are not present, instead the organic part, that is the methyl group, is present and it has 6 methyl group. So, the reaction rate would be slow and it converts to the tetramer. The higher polymerization, or we can say the higher polymers, are not formed in this case. But if in place of methyl group there would have been halogen atoms, then easily the higher polymers would have been formed. Coming on to the physical properties of phosphazines. The trimer, that is NpCl2 whole thrice, has a melting point of 114 degrees Celsius and a boiling point of 256 degrees Celsius at 1 atmospheric pressure. It is readily soluble in organic solvents like ether, benzene, carbon tetrachloride. The tetramer, that is NpCl2 whole 4, it has a melting point of 123.5 degrees Celsius and a boiling point of 328.5 degrees Celsius, and it is less soluble in organic solvents than the trimer. When the solutions are allowed to stand, the polymers get cross linked and slowly a gel formation takes place. Now, the chemical properties of the phosphazines. The first property is the heating effect. On heating to about 150 to 300 degrees Celsius, both the trimer and the tetramer, they polymerize to an elastic product with high molecular weight of the order of 20,000. On further heating to about 350 degrees Celsius, the product gets depolymerized. So, this is the trimer. If it is heated to 350 degrees Celsius, so depolymerization takes place. The second chemical property is the substitution reaction. The chlorine atom in the phosphonitrile chlorides is reactive and it can be replaced by other monovalent groups like halogens, which is fluorine, bromine, or OH, OR, SH, SR, thiocyanate, SCN, NH2, amine, secondary amine, etc. So, we can see here we have NpCl2 whole thrice, that is a trimer. When it reacts with sodium fluoride, what happens? This chlorine atom, it is substituted by the fluorine atom. So, we get NpF2 whole thrice, that is a trimer containing the fluorine. If the same trimer containing the chlorine, it is reacted with sodium alkoxide, this chlorine, both the chlorine atoms, they are substituted by the alkoxy group, that is the OR group. If the same trimer is treated with RMGX, that is the Grignard reagent, what happens? This chlorine, both the chlorine atoms, they are now replaced by the methyl group. And if it is treated by sodium thiocyanate, so the chlorine atom will now be replaced by the thiocyanate group. So, we have NpSCN whole twice, the trimer. The third property is the hydrolysis. The cyclic trimer can be hydrolyzed to trimetaphosphatic acid, which undergoes isomeric change to trimetaimidophosphoric acid. So, this is the trimer. When it is hydrolyzed, that is, it is reacted with water, the Cl group, they are replaced by the OH group. So, this compound is called trimetaphosphatic acid. It undergoes isomeric change and we get trimetaimidophosphoric acid. In this, one of the OH group, it is replaced or it is changed to the carbonyl group at all the 3 phosphorus atoms. Similarly, the hydrolysis of tetramer takes place. This is the tetramer. When it is hydrolyzed or reacted with 8 molecules of water, all the chlorine on this tetramer, they will be replaced by the OH atoms, which undergoes the isomeric change, and one of the OH on the phosphorus, on all the 4 phosphorus, it will be changed to the carbonyl group. This cannot be said the carbonyl group because here it is the phosphorus atom. In carbonyl group, carbon is present. So, we can say phosphorus bonded to, double bonded to oxygen atom. Coming on to the nature of bonding in phosphazines. The trimer halide, that is triphosphazines, have planar ring structure which is resonance stabilized. So, we can see here these are the 2 structures, and this is resonance stabilized. The double, in the first structure, the double bond is present at this position, and in the second case we can see this double bond has changes. So, this is the trimer. We can see these 2 trimers are resonance stabilized, and we can see that double bond is not fixed or it is not localized, but it is delocalized. It keeps on changing its position. The trimer halide, that is triphosphazine, have planar ring structure which is resonance stabilized. So, we can see this is the trimer, that is triphosphazine, and this structure is stabilized because of resonance, and we can see here that the double bond is not localized, that is, it is not present at one position, but the position keeps on changing and the bond is delocalized due to resonance, and hence it is stabilized. The tetramer, that is PnCl2 whole 4, it has a puckered ring structure like that of cyclohexane with alternate phosphorus and nitrogen atoms and with 2 chlorine atoms. So, we can say this is the puckered structure, this is the boat conformation, it is same as that of the cyclohexane, and this is the chair conformation. Again, this is same like the chair conformation of the cyclohexane. Bonding in triphosphazine. All phosphazines contains an unsaturated group. Phosphazine have 2 coordinated nitrogen atom and 4 coordinated phosphorus atom. The 2 coordinated nitrogen atom means that the nitrogen is attached to 2 groups, or we can say 2 atoms, that is the phosphorus, and phosphorus is attached to 4 groups or 4 atoms, 2 halogen atoms, or we can say R groups, and 2 nitrogen atom, therefore it is 4 coordinated. 2 of the 5 valence electrons on nitrogen form sigma bond. Both nitrogen and phosphorus, these have 5 valence electrons. In case of nitrogen, 2 of the 5 valence electrons, they form sigma bond, and in case of phosphorus, 4 of the 5 valence electrons, they form sigma bond. So, therefore, 3 electrons on nitrogen and 1 electron on phosphorus are left. 2 of the remaining electrons on nitrogen are assumed to occupy a non-bonding orbital, while the third electron on nitrogen interacts with 1 electron on phosphorus atom to form a pi bond. So, we can see here this nitrogen, it has 5 valence electron, phosphorus also have 5 valence electrons. This nitrogen, it has 1 lone pair of electrons, or we can say a non-bonding pair of electrons which is present in non-bonding orbital. 2 of the electrons on nitrogen, they form sigma bond. We can see in this figure, this is the nitrogen, it has 1 lone pair of electron, these are 2 sigma bonds. So, 2 electrons on nitrogen, they participate in the formation of these 2 sigma bonds. 1 electron is left free. So, this is the electron which is left. In case of phosphorus, it is 4 coordinated. So, 4 of its electrons, they are used in formation of sigma bonds. So, we can see it forms 4 bonds, one with this nitrogen, 1 bond, or we can say 1 sigma bond with another nitrogen which would be present here, and these 2 sigma bond with the 2 R groups. So, 1 electron is left on this phosphorus. The skeletal bond angles on phosphorus in cyclotriphosphazenes is approximately equal to 120 degrees. Phosphorus nitrogen phosphorus and nitrogen phosphorus nitrogen bond angles in the rings are 121.6 degrees and 118.4 degrees respectively. The skeletal nitrogen atoms in cyclophosphazines are weakly basic and can be easily protonated and can form coordination complexes when electron releasing groups are present on phosphorus. So, from this figure we can see the bond angles and the bond distances. So, this angle, that is the angle between the R, phosphorus and chlorine, is 108 degrees. Angle between nitrogen, phosphorus and nitrogen is 118.4 degrees, and the angle phosphorus nitrogen phosphorus is 121.6 degrees. The bond distance between the phosphorus nitrogen is 158 picometers, and all the bonds, that is the phosphorus nitrogen, all the bonds are equal. In this figure we can see that phosphorus, it contains 5 valence electrons. The 4 are being used in formation of the sigma bond, 2 with the chlorine atoms, 2 with the nitrogen, and 1 is left free. In case of nitrogen, it also contains 5 valence electrons. The 2 are used in the formation of sigma bonds, 1 is in the non-bonding orbital and 1 is left free. Spectral effects like bathochromic shift, which are associated with the organic pi electron systems, such type of effects are not observed in the case of phosphazines. Cyclotriphosphazenes skeleton cannot be electrochemically reduced like in the case of organic aromatic compounds, which can be easily reduced. So, these were the difference between the organic and the phosphazines, that is the organic pi groups and the phosphazines. Based on these evidences, it can be stated that the phosphorus nitrogen bond differs significantly from the aromatic sigma pi system, in which there is extensive delocalization through the p pi bonding. The d p pi bonding model for cyclotriphospazene. The cyclic triphosphazene consists of planar 6-membered ring. The sigma bond framework is made up of overlapping bond orbitals from phosphorus and nitrogen. Bond angles suggest sp2 hybridization of nitrogen and sp3 hybridization of phosphorus. 2 of the sp2 hybrid orbitals on nitrogen containing 1 electron each are used for sigma bonding, and the third contains a lone pair of electrons. 1 electron is left unhybridized, that is in the pz orbital of nitrogen. Similarly, 4 of the sp3 hybrid orbitals of phosphorus containing 1 electron each are used for sigma bonding. 2 with nitrogen atoms and 2 with the halogen atoms, leaving one unhybridized orbital containing 1 electron. This is the nitrogen. We can see the 5 valence electrons. The 4 are being sp2, the 4 are sp2 hybrid, that is the one lone pair in the s orbital and 2 electrons in the p orbital. They mix together to form sp2 hybridized orbitals. One is left unhybridized, which is present in the pz orbital. Similarly, in phosphorus we can see the 5 orbital. The phosphorus also uses its d orbital system. The 4 electrons in the one in the s orbital and 3 in the p orbital, they mix together to form sp3 hybridized orbitals, and the electrons are present in these 4 sp3 hybrid orbitals. The 5th electron, which is present in the d orbital, is unhybridized. This we can see from this figure. The 3 orbitals in black color, these are sp2 hybrid orbitals, one containing the lone pair of electron and 2 containing single electron, which are used in the formation of sigma bond. The blue orbital, it is the unhybridized pz orbital, which contains 1 electron. This unhybridized orbital on nitrogen and one on the phosphorus, which is the d orbital, these two they combine to form the pi orbital. So, the pi orbital is also formed between nitrogen and phosphorus, which is formed between the unhybridized orbital of phosphorus and the unhybridized orbital or electron of nitrogen. Bonding in cyclotriphosphazenes involves 2 types of pi bonding: out of plane heteromorphic pi bonding and in plane coordinate pi dash bonding. Out of plane heteromorphic pi bonding. Pi bonds are formed between the phosphorus and nitrogen using valence electrons in the 3d orbital of phosphorus and the pz orbital of nitrogen. As I have already told, the 2 orbitals which are left unhybridized, the electron present in them, they form the pi bonds. The dxz orbital of phosphorus atom overlaps with the pz orbital of nitrogen to form d pi p pi bond. This type of d pi p pi bonding is called heteromorphic or pseudo aromatic pi bonding. Pseudo aromatic because in case of aromatic compounds, that is the carbon compounds, the bonding is or the pi bonding is between the p orbitals. So, we have p pi bonding. Here we have the bonding, the pi bonding between the d orbital of electron present in the d orbital of phosphorus and the second electron present on the p orbital of nitrogen. So, we have d pi p pi bond. This is the structure for the heteromorphic or pseudo aromatic d pi p pi bonding. Here we can say this is the phosphorus atom which contains the d orbital, and these two are the nitrogen atom which contain the p orbital, and the pi bonding takes place among this, the d orbital of phosphorus and the p orbital of nitrogen. So, we have d pi p pi type of bonding. Pi dash bonding by donation of the lone pair of electrons of nitrogen into the vacant dx square minus y square and dxy orbital of phosphorus. So, this is the pi interaction in xy plane of sp2 nitrogen. This is these two are the nitrogen, and the dxy, this is the dxy orbital of phosphorus. This is pi dash interaction in the xy plane of sp2 hybridized nitrogen. These two are the sp2 hybridized nitrogen, and this is the dx square minus y square orbital of phosphorus. So, this is pi dash interaction and this is pi interaction. Coming on to the Dewar and co-worker models. According to the Dewar and co-worker models, dyz orbital, which is perpendicular to dxz orbital, can overlap with the pz orbital of nitrogen. Both these orbitals contribute equally to the pi bond. These are heteromorphic when phosphorus nitrogen d pi p pi bonds with the dxz, and are homomorphic when the phosphorus nitrogen d pi p pi bonds with the yz. So, we can see in this figure, this is the heteromorphic pi interaction of pz orbital of nitrogen and dxy orbital of phosphorus. This is the dxy orbital of phosphorus. When it interacts with the pz orbital of nitrogen, this is the heteromorphic pi interaction. The second one, this is the homomorphic pi interaction, because in this case the p z orbital of nitrogen, these interact with the d y z orbital of the phosphorus. Each nitrogen has a 3 center localized bond which is known as island of pi character. The nodes will be present at phosphorus. Nodes means that electrons are absent at particular place. The nodes will be present at phosphorus atom as this island is interrupted at each phosphorus atom. So, cyclotriphosphazenes do not show broad delocalization effects like benzene, which has simple p pi bonds. This was all about the nature of bonding in phosphazene. Coming on to the uses of phosphazines. Phosphazines are used as catalyst in the manufacture of silicons. Thin films of polyaminophosphazenes are used to cover severe burns and serious wounds, as they prevent the loss of body fluid and keep germs out. Phosphonitrile halides are used as rigid plastics, expanded form and fibers, because they are waterproof, fireproof and are unaffected by oil, petrol and other solvents. These are used as flexible plastics which are useful fuel hoses and gaskets, because they retain their elasticity at low temperature. So, this was all about the phosphazines. Coming on to the summary of today's episode. In today's episode, we have studied phosphazines, their different methods of preparation, their physical and their chemical properties, the structure of phosphazines, nature of bonding in phosphazines. We have also studied the d pi p pi bonding model of cyclotriphosphazenes and the Dewar and co-worker model of phosphazines, and also we have studied the uses of phosphazine. So, with this we end with the series on silicons and phosphazines. In this series we have studied polymers, glass transition temperature, silicons, their nomenclature, preparations and properties, equilibration and ring opening polymerization of cyclosiloxanes, silicon fluids, silicon elastomers, silicon resins, their preparations, properties and uses. Further, we have studied phosphazines with special emphasis to cyclic trimer and tetramer, their preparation, their properties and nature of bonding in phosphazines was also studied, and in the end we studied the uses of phosphazine. So, with this we end with this series on the silicons and phosphazines. Thank you.